So this whole protocol is about sending one bit at a time, right? First you're sending the address bits, the direction bit, then you're sending the data bits, and so on. So you have to be able to send one bit at a time on these lines. So let's just show how that goes on. Remember that there are two wires, SDA and SCL. And the data, whatever bit you're going to send, that's going to go on the SDA line. But while the SDA line is going, the SCL line is it's a clock, so it's going up and down. So this is showing how sending a bit might look. Now, you can see at the bottom the SCL, that's low, then high, then low. That's one clock pulse. The SDA line, however, that can change from 0 to 1, 1 to 0. Now, the SDA, depending on what bit you're sending, you might be sending a 0 or 1. So notice that in the timing diagram picture here for the SDA, you can see that the SDA, you have it on both low and high. That's representing the fact that it could be 0 or 1. Okay? But you'll notice that there are two places where it crosses, where it starts out low-high, then it crosses, and then it's low-high again, then it crosses again. So those crosses, what they mean in this diagram is that those are the times when SDA can change value. So all this diagram is trying to say is that, say you want to send a bit, right, 0 or 1. So you put that on SDA. But SDA is sampled by the receiver on the rising edge of SCL. So what matters, the value of SDA that matters is the value of SDA that SDA has right when the clock edge is going high. So you see that where the SCL line goes from 0 to 1, the value of SDA at that time is what counts. So the sender, the master, say, whoever's doing the transmission, they have to apply a value on SDA before the SCL goes high and hold it while SCL is going high, right? So, and then that is the value that the receiver is going to accept. So SDA is sampled by the receiver on the rising edge of the clock. Also, there's a rule about this protocol that SDA, the data line, has to be held constant as long as the clock is high. And you can see that in this picture. The SDA line, it can change values, but notice that the changes in value happen either before the clock edge, before the clock goes high, or after the clock goes high, right? Always when the clock is low, that's when the change happens. There can't be a change during the time when the clock is high. That's just a rule. The only time you can break that rule is if you're doing a start condition or a stop condition. Those conditions explicitly violate those rules, right? A start condition is where the SDA goes low while the clock is high, and stop is where it goes high while the clock is high. So, but if you're sending data, you're sending actual data, then the rule is that the SDA line has to be held constant the whole time that the clock is high. An acknowledge bit. So what this means is, okay, so the way this protocol is organized around sending bytes. Okay, all data is sent 1 byte at a time. So you do a start condition, then you send a byte. The first 7 bits of the byte are the address, and then the next bit is the next 1 bit is the direction. But altogether, that's a chunk of 8 bytes. Then after you send that byte, let's say it's a write transaction, then you start sending data bytes, 1 at a time, 1 bit at a time, but you send them in chunks of 8. Now, what happens is after a chunk of 8 is sent, after a sequence of 8 bits is sent, the receiver has to acknowledge that it received the 8 bits. Now, this is for error checking, essentially, because you never know what kind of error might have happened in communication. So if it didn't receive the 8 bits, then you need to restart your communication. So after every chunk of 8, the receiver has to transmit what's called an acknowledge bit. Now, what that means is, let's say we've got the SDA line, SCL line. SCL is pulsing high-low. And SDA, say the master is transmitting to the slave, okay? So it transmits 8 bits, and we've numbered them up there on the SDA line. 1, 2, 3, ... right? Until you get to bit 8. So once it sends out all 8 of these bits, at that point, for 1 SCL clock pulse, the master does not drive the SDA line. It's up to the slave, it's up to the receiver, which if the master is doing transmission, it's the slave, but it's up to the receiver at that point to pull the SDA line low. That's called acknowledge. See where it says ACK? Notice that the SDA line is low when it says ACK. So at that point, for that clock pulse, that SCL clock pulse, the receiver has to pull that clock cycle, that SDA line low. That's an acknowledge. If it doesn't do that, then the sender has to assume that something went wrong and restart the communication. So after each byte is sent, the receiver must acknowledge by pulling that SDA line low, and the transmitter releases once the transmitter. Excuse me. The transmitter has to release the SDA line so the receiver can pull it low. Must be low for 1 pulse of the clock, or else your transmission's aborted. So typical I2C transaction. very short I2C transaction. Here's what it would look like overall. There's a start condition, that starting blue block right there. That's you initiate everything with the start condition. Then you send 8 bits, the address bits, 7 address bits plus a direction bit, so that's 8 bits. Then there's an acknowledge bit, the ACK right there. Then you send 8 more data bits, and then there's another acknowledge, and then you can stop. Now this is short, right? It's only transmitting 1 data byte. This could be extended. You could have many data bytes, right? In this case, I just did 1. So this is sort of a typical I2C transaction, what it looks like on the SDA lines. Yeah, each slave has a unique 7-bit address. Direction is 0 is a write, 1's a read. And ACK happens after every byte. Thank you.